We will discuss the following topics in this chapter: objectives of learning, Hebb's rule, delta rule, supervised learning, and unsupervised learning. What is learning? The various definitions given by the pioneers given below for learning. Herbert Simon, 1983. Learning denotes changes in a system that enables a system to do the same task more efficiently the next time. Marvin Minsky, 1986. Learning is making useful changes in the workings of our minds. Ryszard Michalski, 1986. Learning is constructing a modifying representation of what is already being experienced. Michel, 1997. A computer program is said to learn from experience E with respect to some class of task T and performance measure P, if its performance at task in T, as measured by P, improves with experience E. Learning agents. An agent is an entity which is capable of perceiving and acts as an action. An agent can be viewed as perceiving its environment through sensors and acting upon the environment through actuators. In computer science, an agent is an assisting software agent for the users and acts in performing computer-related tasks. Learning methods in neural networks. The learning methods in neural networks are classified into three basic types. These types are classified based on supervised learning, unsupervised learning, reinforced learning. The classification of learning algorithms is given here. Delta rule. Basic delta rule. Delta rule is otherwise known as the least mean squares, LMS, or Woodrow-Hoff rule. The basic delta rule is given by del Wij equal to alpha of Tj minus Yj xi, where Tj is equal to the teacher value or desired value of unit j. Yj is equal to the actual output for unit j. Alpha is equal to learning rate. Delta Wij is equal to alpha delta xi, where del equal to Tj minus Yj. The difference lies between the desired or target output and actual output. The delta rule modifies the weights appropriately acceptable for both continuous and binary inputs and outputs. The delta rule minimizes the squares of the differences between the actual and the desired output values. The squared error for a particular training pattern E equal to summation j of Tj minus Yj the whole square, where E is a function of all weights. The gradient of E is a vector consisting of the partial derivatives of E with respect to each of the weights. This vector gives the direction of most rapid increase in E. The opposite direction gives the direction of the most rapid decrease in the error. The error can be reduced most rapidly by adjusting the weight Wij in the direction of minus rho E divided by rho Wij. Generalized data rule. In a multi-layer network, the determination of the error is in a recursive process, which starts with the output units and the error is back-propagated to the input unit. Therefore, the rule is called error backpropagation, BP. Del Wij equal to alpha del Jxi. Del J equal to Tj minus Yj f dash y minus in J, where y minus in j equal to summation wij xi plus b. Hebb's rule. Hebb's law states that if neuron I is near enough to excite neuron J and repeatedly participates in its activation, the synaptic connection between these two neurons is strengthened and neuron J becomes more sensitive to stimuli from neuron I. Hebb's law can be represented in the form of two rules. If two neurons on either side of a connection are activated synchronously, the weight of that connection is raised to a higher level. If two neurons on either side of a connection are activated asynchronously, the weight of that connection is decreased. Hebb's law provides the basis for learning without a teacher. Hence, learning is meant to be a local phenomenon occurring without obtaining feedback from the environment. Hebbian learning in a neural network. Using Hebb's law, we can express the adjustment applied to the weight Wij at iteration p in the following form. Del Wij of p equal to f of yj of p, xi of p. As a special case, we can represent Hebb's law as follows. Del Wij of p equal to alpha yj of p xi of p, where alpha is the learning rate parameter. This equation referred to as the activity product rule. Hebbian version of learning implies that weights can only increase. To resolve this problem, imposing a limit on the growth of synaptic weights can be done by introducing a nonlinear forgetting factor into Hebb's law. Del Wij of p equal to alpha yj of p xi of p minus phi yj of p wij of p, where phi is the forgetting factor. Forgetting factor usually falls in the interval between 0 and 1, typically between 0.01 and 0.1, to allow only a little forgetting while limiting the weight growth. Hebbian learning algorithm. Step 1. Initialization. Set initial synaptic weights and thresholds to small random values, say in an interval 0, 1. Step 2. Activation. Compute the neuron output at iteration p. Yj of p equal to summation of I equal to 1 to n xi of p wij of p minus theta j, where n is the number of neuron inputs and j is the threshold value of neuron j. Step 3. Learning. Update the weights in the network. Wij of p plus 1 equal to wij of p plus del wij of p, where del wij of p is the weight of correction at the iteration p. The weight correction is determined by the generalized activity product rule. Del wij of p is equal to phi yj of p of lambda xi of p minus wij of p. Step 4. Iteration. Increase iteration p by 1. Go back to step 2. Hebbian learning. Example. To illustrate Hebbian learning, consider a fully connected feed-forward network with a single layer of 5 computation neurons. Each neuron is represented by a McCulloch and Pitts model comprising the sign-activated function. The network is trained on the following set of input vectors.
Initial and final state of the network. The initial and final state of the network is shown in the below picture.
Initial and final weight matrices. A test input vector or prob is defined as x is equal to matrix 1, 0, 0, 0, 1. When this prob is presented to the network, we obtain the following. Supervised learning. A teacher is readily available during the learning process and helps in producing expected output. In the supervised training, both the inputs and the outputs are provided. The processing of the inputs by the network compares its resulting outputs against the desired outputs. Errors are then propagated back through the system, causing the system to adjust the weights which control the network. This process occurs over and over as the weights are continually tweaked. The set of data which enables the training is called the training set. During the training of a network, the same set of data is processed many times as the connection weights are ever refined. Example architectures, multi-layer perceptrons. Learning algorithm for training perceptron. The training of perceptron is a supervised learning algorithm where weights are adjusted to minimize error whenever the output does not match the desired output. If the output is correct, no adjustment of weight occurs.
That is Wij power k plus 1 equal to Wij power k.
If the output is 1 but should have been 0, the weights are decreased on the active input link.
That is Wij power k plus 1 equal to Wij power k minus alpha into xi.
Instead of the output 0, it should have been 1. Then the weights are increased on the active input link.
That is Wij power k plus 1 equal to Wij power k plus alpha into xi, where Wij to the power k plus 1 is a new adjusted weight. Wij to the power k is the old weight. Xi is the input and alpha is the learning rate parameter. Alpha small leads to slow and alpha large leads to fast learning.
Supervised learning algorithm. Step 1. Create a perceptron with n plus 1 input neurons x0, x1 up to xn, where x0 is equal to 1 is the bias input. Step 2. Initialize weight W is equal to W0, W1 up to Wn to random weights. Step 3. Iterate through the input patterns xj of the training set using the weight set. That is, compute the weighted sum of inputs
Net j equal to summation of I equal to 1 to n xi into wi
for each input j. Step 4. Compute the output yj using the step function. Yj equal to f of net j equal to 1 if net j greater than or equal to 0 and 0 if net j lesser than 0, where net j equal to summation of I equal to 1 to n into xiwij. Step 5. Compare the computed output yj with the target output yj for each input pattern j. If all the input patterns have been classified correctly, then output read the weights and exit. Step 6. Otherwise, update the weights as given below. If the computed output yj is 1 but should have been 0, then wi is equal to wi minus
alpha xi.
I is equal to 0, 1, 2 up to n. If the computed outputs yj is 0 but should have been 1, then wi is equal to wi plus
alpha xi,
I is equal to 0, 1, 2 up to n, where
alpha.
is the learning parameter and is constant.
Step 7. Go to step 3. End.
Unsupervised learning. Absence of the teacher is observed. In unsupervised training, the network is provided with inputs but not with desired outputs. The system must decide what features are going to be used to group the input data. This is often referred to as self-organization or adaptation. For example architectures, Cohen and ART. Approaches to unsupervised learning include clustering. Example, K-means mixture models, hierarchical clustering. Approaches for learning latent variable models such as expectation maximization algorithm, method of movements, blind signal separation techniques. Example, principal component analysis, independent component analysis, non-negative matrix factorization, singular value decomposition. Unsupervised learning, clustering. Clustering is a way to form natural groupings or clusters of patterns. Clustering is often called as unsupervised learning. Example, 3 natural groups of data points, that is, 3 natural clusters. Clustering is one of the most utilized data mining techniques. The data have no target attribute. The data set is explored to find some intrinsic structures in them. Distance functions. Euclidean geometry is the study of relationships between angles and distances in space. An n-dimensional Euclidean space or an n-space is the extensions of mathematical spaces to any dimension. Let R denote the field of real numbers. The space of all n tuples of real numbers forms an n-dimensional vector space over R, denoted by R to the power n. An element of R to the power n is written as x is equal to x1, x2 up to xi up to xn, where xi is a real number. Similarly, the other element y is equal to y1, y2 up to yi up to yn. The vector space operations on R to the power of n are defined by x plus y is equal to x1 plus y1, x2 plus y2 up to xn plus yn, and ax is equal to ax1, ax2 up to axn. The standard inner product, that is dot product or R to the power n given by x into y equal to summation of I equal to 1 to n of x1 y1 plus x2 y2 up to xn yn
is a real number.
The product defines distance function or metric on R to the power n by d of x, y equal to parallel of x minus y equal to root of summation I equal to 1 to n of xi minus yi the whole square. The interior angle theta between x and y is given by theta equal to cos power minus 1 of x into y divided by parallel x and parallel y. The inner product of x with itself is always non-negative. Parallel x equal to root of summation I equal to 1 to n of xi minus yi the whole square.
Conclusion. In this chapter, we have covered the following in detail.
Objectives of learning, Hebb's rule, delta rule, supervised learning and unsupervised learning.